Hello, everyone. This is Yogeshwar. So I think we'll get started in another minute or so. Yeah. Okay. I think we can get started now. Welcome, everyone. Week 4. So today we will be covering some of the aspects of feature scaling. We will be talking about normalization, standardization techniques, regression model evaluation, and then we will have like a walkthrough of a Jupyter notebook wherein we will cover some of the scikit-learn APIs for these techniques that we will discuss today. To begin the lecture, I just wanted to check back with Peter if you have anything to add to our previous conversation on the decision trees, Peter?
Yeah, can you hear me?
Yes.
Okay, so
Yeah, I was wondering whether you had something to show today. If not, that's totally fine.
I do.
Okay, awesome.
I can talk for 10,
Okay,
15 minutes.
definitely. Do you have slides and I can share the...
I can share it from my computer if you are.
Okay, yes. So let me stop sharing and can you try?
Yep, just a moment.
Sure. Yes, we can see.
All right, good. So I will. I have just a few slides, and then I will try to show some things in practice. I never did a presentation on this project before, so this is kind of ad hoc. And this is really in a work in progress. We have a shared project with, or a collaborative project with the mechanical department and biomedical department to basically create some assistive clothing which can reduce this low back pain. Basically, the targeted audience or the actual application is workers in a warehouse or anybody who as part of his regular job has to lift heavy weights. Another application domain is soldiers and people like them. Anyway, so what the project tries to do is happening in two distinct phases. The first question that we are trying to answer or trying to solve is to come up with very accurate predictors which can tell us how much loading is happening on the spinal cord. So this is really just an observation, and we would like to build a model, a machine learning model, which uses variable sensors, inertial measurement units, or little pressure sensors embedded into the sole of the shoes, things like that. And based on these measurements, first we would like to estimate, especially in the lumbar region, how much force is being applied in between those discs in the spinal cord. So this is phase one. Phase two is to develop some garment, a smart garment, which has some actuation built into it. So it's a small motor or a tension or a spring, but actuated by a motor, which can decrease this amount of loading on the spine. So this is a lofty goal. Even the first one is a very lofty goal because we can put zillions of sensors on a single person, even if it doesn't make sense. But from these sensors, how do we estimate that loading on the spine? And I think, and to be honest with you, with all of you, this is where I think the weakness or the real hard problem of this project lies. And I think it's good to see these issues coming up in this course, because nothing like in the textbook when it comes to reality. In this particular project, the real problem is how to get data on the ground truth. How do you get if you are thinking about supervised learning, because in phase one, basically what we are trying to do is a regression problem with a supervised learning approach, right? We are trying to build a regression model which can estimate that load between the disks. But the problem is that we don't have the ground truth. We can just have an indirect estimation of the ground truth, and the way people do it at the mechanical and biomedical departments is we have a nice room with full of cameras, and we put markers, 50, 60 markers on the test subject while he's doing these movements, and we are reconstructing the whole skeletal model, the animated skeletal model of these movements. And based on that, and using just physical principles, we are calculating the spinal moment, the moments acting on that spine. But this is an indirect method, and this is why I said that we don't have real ground truth data. Although I went through this experiment, I did the exercises for 8 hours, and I'm still not complaining that we don't have a better estimate for the ground truth, because the alternative would be to embed some pressure sensors in my spinal cord. So I'm kind of happy that we don't do that. But that being said, the problem is that even the absolute ground truth data that we use for training and evaluating in the testing data set is kind of an indirect method. Other than those markers, we put a lot of wireless sensors on the human test subject. So these are these inertial measurement units and pressure sensors, things like that. Actually, I have a short video. It doesn't have a sound, so you don't need to hear anything here. But this is what test subjects are doing for 8 hours in the lab. We are collecting a lot of data with all these sensors, and obviously you can see on my arms, these are the markers, the visual markers that we use to basically estimate calculate the ground truth. So right now, in the phase one, the question is really this regression problem to estimate the load on the spine. And let me go to the details, and I probably should keep it short. I'm going to share my web browser just for a moment. Yep. So jumping to the actual implementation, after these data collection sessions, I have a huge data set. The current data file is a 2 gigabyte CSV file, and it has 300, 400 different columns for those sensors that we could cook up. More than actually what we need. So I have columns which represents the readings of those sensors, and a few columns which are the target variables. Not just a single target variable, because we have different targets for the different directions, the different angles, how the spine is being flexed. It's not a big difference. Now, the current method is very simple, or the current approach is very naive. Even though we are capturing a time series data, the model that we would like to build is a model that can estimate the instantaneous load on the spine based on the instantaneous measurements of these sensors. So as we are capturing these time series data, synchronized time series data across all the sensors, every single data sample across all the sensors will become a single sample in our training and testing data set. So this data set contains 500,000 samples currently, and it's just about 2 or 3 test subjects at this moment. We are working to extend this data set. And I'm doing the initial experiments and training in notebooks. I started to work with Google Colab. It's a great tool, but to be honest with you, once your data and model becomes large or significant of a significant size, the Google Colab approach just not going to scale. It's a single instance. You get it for free, but it just does not have the power, the computational power. If you really have large data sets and you want to do a lot of parallel experiments, for example, for hyperparameter optimization. So after half a year, I had to switch over to a different approach. It is not just a barebone Jupyter notebook. I'm actually using, can you see my screen with Amazon SageMaker?
Yes,
Good.
yes, we can see it.
Okay, so I'm using Amazon SageMaker. Amazon SageMaker is part of the AWS offerings, Amazon Web Services offerings. It provides you notebook instances, but the notebook instances are just the front-end interface for training resources. So from these notebook instances, which are hosted on the Amazon cloud, from those notebook instances, I can launch training jobs which will spin off and will be running in the cloud in Dockerized containers. And these containers are actually maintained and managed by Amazon. So Amazon built up a lot of machine learning algorithms and packaged them as containers. But it's not that important for today's discussion. I just wanted to show you that how one particular notebook looks like. It's very similar what Yogesh is going to show you, I'm pretty sure. And instead of, I'm not going to be able to explain cell by cell. I'm not even trying to do so. I would like to just pinpoint one important aspect in this whole story. So this is a regression model. This notebook tries to build up a regression model which tries to estimate the spinal loading or the moment on the spine based on measurement data. And what I would like to show you is that among all these code, there is a single line in this entire code base, and this is here, which is actually about the machine learning model. It uses a gradient boosted method. It is based on the decision trees that Daniel and Yogesh was talking about last time and probably going to talk today. But we are training several, in this particular case, 100 decision tree models on top of each other. But the point here is that if I change this single line of the code, I can replace the gradient boosting method with regression trees into a linear regression model or into a neural network model. So what I'm trying to say is that when you are writing typical machine learning applications, 90x% of your time will be about the preparation of the data, to select the features, to select test and train sets, and run the experiments. It's really not about building up the model. That's typically the least amount of code and sometimes the least amount of effort. In this particular project, but it happened to me in another machine learning project which aimed at gunshot localization, a very different project, but I ended up in the same problem. And this problem is about how you select the features and how do you evaluate your models across different test and train allocations, because the generalization of the model, how well it will perform an unseen test set is much more important than you think. Okay, so this is a problem that will coming up again and again. You are happy with your training results, but it just fails miserably with the test set. And therefore, it's super important to try your methods in various combinations, how unforeseen test sets perform with that model. So I have a small rant and I'm trying to wrap it up soon. I have a small rant against notebooks. So I have this love and hate relationship with Jupyter notebooks. I happen to teach Python for engineering students as well, and I experienced the same problem there that I experienced myself during work. So Jupyter notebooks are pretty neat to explain stuff, especially if your audience knows how to read Python programs. It's not so great if you want to show your results to people who don't know or don't want to know about Python. That's the first issue. The second issue is more problematic or more fundamental. Jupyter Notebook really does not encourages you to write maintainable code. When you are writing your code in those code cells, you end up and you are very tempted to store everything in global variables, which is further complicated by the fact that you can evaluate those cells out of order. And if you modify your cells, still old variables can linger in the memory in the kernel of the Jupyter Notebook, on the Jupyter Notebook server, which can create very nasty problems. So long story short, I am not a big fan of Jupyter notebooks for the long run. So what else do I do? And this is where I would like to just show some alternative stuff here. One thing I absolutely love, especially to share my results with my collaborators at the mechanical department, is called Streamlit. Streamlit is a web application framework in which you can write your machine learning code as a Python script. The framework automatically creates a web interface based on the results of your Python script, and it also provides you interactions with that script. So for example, this is actually the very same code that I developed for the Jupyter notebook, but embedded in this Streamlit script. So what is happening on the left-hand side, I can select which data set I want to work with. Also, I can select which variable, target variable I would like to estimate. I can also down select which features I would like to use, which sensors I would like to use. And every time I make some modifications on the left-hand side, you can see that in the right-hand side, in the main area, the results, the estimation results are being re-evaluated. Basically, my Python script, which contains all the code for training and testing, will rerun, and the results will be shown here. So this particular figure, the scatter plot, is about the high-level results. This shows us how our regression model works, how the estimated spinal loading is correlated with the actual measured data. So Streamlit is, I highly suggest to eventually try out Streamlit, especially if you agree with my statement about the messiness of Jupyter notebooks. The other tool I would like to share, and I'm really shut up, is called Orange. And my collaborators at the mechanical department actually fell in love with this tool. This is kind of a GME-like tool for machine learning and data science. It is also written in Python, and it is based on the scikit-learn library that Yogesh is teaching us about. But instead of writing the code by hand for data preprocessing and using the the normalization, standardization, and eventually the machine learning methods, you can do all these things just in a graphical model. It's very easy to use and very intuitive. For example, in this model, I put together, I compared different machine learning model on this spinal data set. I have linear regression, a ridge regression, lasso regression, which are modified linear regression model, a support vector machine model, a random forest, and a neural network. And everything is being evaluated by this tool on the fly. So I can compare how, for example, a neural network model compared to a random forest, compared to a k-nearest neighbor model, or an SVM model perform. And obviously I can train the hyperparameters, whatnot. And as I said, the benefit here is that you can really just put together a model like this graphically. You can still have access to the hyperparameters. Basically, these are the parameters in scikit-learn of these trainers. But once I cooked up this graphical model and showed it to my collaborators who don't know how to think in Python, they have a much better understanding what I'm talking about. So sorry about this mess, but I just wanted to share you how a machine learning project looks like in practice, and probably what are the pitfalls. And again, I caution you not to completely fall in love with Jupyter Notebook. There are tools beyond or alternatives to that. So thank you for listening.
Yeah, this is awesome. Thank you, Peter. I mean, this is the whole purpose of this seminar series, is like wherein we can present our new findings that we gather and present it to the audience over here, and we all can learn from each other some of the new things that are happening in this domain. So thank you very much for introducing us to these new tools, and as well as the project that you are working on. So that's neat.
Great, thanks.
All right, let me quickly share my screen here. Okay, so as Peter pointed out, that for training the model, you have to do a lot of pre-processing of data. It's not straightforward, and not necessarily you can directly use the data as is. So is this screen visible to all? Just first question.
Yes.
Okay, nice. Yeah. So one of the first steps in pre-processing is something called as feature scaling. So let's look at why we need feature scaling. So as you all know, like for different domains, there could be different features, and each of the features might have different kinds of units and ranges associated with it. So for instance, you may have like units in kilograms, square feet, square meter. The features could be represented in millions, for instance. So 1 million unit, or say in 10,000 unit, and so on. Similarly, you could have features which are of different varieties, like they represent, for instance, an age, and other feature might represent an income. So over here we can see that the scales of these different features do not necessarily like give a good view to the end users to interpret like how will one feature affect the result or the prediction that we are trying to come up with. So so we need some way of like putting the scales, or adjusting the scales of these input features. And one of the approaches that we will be doing, looking at today, is called feature scaling. And in that we will cover techniques such as normalization and standardization. So there are some machine learning algorithms which are very sensitive to the scale. So some of the machine learning algorithms, such as neural network regression, which are using gradient descent based algorithm for finding the solution. So those are really sensitive to the differences in the feature scales. There are other algorithms such as those based on Euclidean distances, such as the KNN, SVM, K-means. So these are the ones that we will cover in our coming class. But those are also like very sensitive to the way the features are represented in the input side, and also the principal component analysis, another machine learning technique. So for all these, if you don't kind of scale the units of different features, then your result output can drastically vary from the ones which is an unscaled unit. There are also some of the machine learning algorithms which are not susceptible to these scale differences. So for instance, in decision tree kind of algorithm, these are not sensitive to the differences in the scales, because the way the decision tree, like we covered last time, was that it is based on each feature, and based on each feature, we decide whether we want to traverse, or so the decision is based on the feature value and not necessarily the whole scale. So with respect to the gradient descent, I just want to quickly, like this is a new term, so I just wanted to quickly introduce what is the gradient descent. So in a linear regression kind of scheme, wherein we have an equation of a line which is like y equals mx plus c. In that kind of equation, when we are representing this x and the y, the dots over here, so we want to come up with a line that will cover most of these points. So the way the gradient descent works is like it tries to find out, select the value of m and c in that equation, which is y equal mx plus c, and it iteratively computes the value of y, and the process continues until and unless we find a point which has the least error with respect to the predicted value. So that's how the gradient descent optimization algorithm at a high level works. So even though linear regression, as Peter had talked about in two or three classes before, is not necessarily affected by the scaling, there is definitely more time that is spent on in traversing this iterative process. So the performance, the model performance might not change, but definitely the learning speed will increase if you don't kind of scale the feature values. So scaling is beneficial, and we'll see a couple of techniques how to go about doing the feature scaling. So so the scaling not necessarily just applies to the input data set. So whenever we scale the input features, we also want to make sure that we descale them to its previous notion. So we have to do scaling as well as descaling. So scaling happens in the pre-processing stage, and we'll have to do some denormalization or descaling at the output end, so that whatever values you are kind of scaling, they should represent the original descale value. So the descaling is also important. So let's look at two techniques for feature scaling. The first is the normalization technique, and the second one is the standardization technique. So in normalization technique, basically what happens is we have a range of input values, and what we try to do is accommodate that scale, the input values, which may vary from like thousands or millions, and try to fit them in a range which goes from 0 to 1. And the way it is calculated is we take the x mean, which is the minimum value of a given feature, and the max would be the max range. So for instance, if you have a feature, say the cost of a house. So the cost of a house, if the range is from say $10,000 to $10 million, for instance. Then with using the normalization technique, we can scale that down and fit it in the range from 0 to 1. So that's this normalization technique. And so this kind of illustrate with an example. So over here we have the original data set, wherein the values range from 0 to 6. And when we kind of normalize that, we are kind of fitting the input data set from 0 to 1, which is seen on the right hand side. So that's what scaling means in this context here. The scaling is also like in scikit-learn, it is invoked using the min-max API, and which we will look in the coming slides. The second technique is called as standardization or z-score transformation. So in this, basically we transform the input data set in a distribution which is centered around a mean of 0 and having a standard deviation of 1. Let's look, and this is the formula for calculating that, but let's look with an example how the input data set will vary. So we have over here an input data set, which the blue is like a raw data. And on the x-axis, you can see that the data is ranging from 0.4 to 0.8. Similarly, on the y-axis, you can see that the data is ranging from 200 to 700. But when we apply the Z transformation or the standardization technique over here, the data kind of spreads around the mean 0 over here. So the bottom half of the graph, which you are seeing over here, is the values go from 0 to 1 and 2 and so on. So that's what the scaling of features mean in this context. So some of the scikit-learn APIs that is common for applying this scaling is first one is something called a standard scalar. So standard scalar basically does the Z transformation. So this just gives an example wherein the data is going from 0, 1, that's the input data. And when we try to fit this in a scalar, like by calling the standard scalar module and apply the fit. Okay, I didn't print the value over here, but basically it tries to fit them in, it will fit with the mean of 0 and spread that data when you are using the standard scalar. Similarly, so that's the scaling, but we also have to descale it. So there is something called inverse transform, which scale backs the data to the original representation. So this is useful when used in the post processing step. So you have the pre-processing step, wherein first you take the raw data, transform it into using the scalar API, train the model and do the prediction and everything. And once the prediction is calculated, which perhaps maybe in the range of 0 to 1, for instance, then we want to represent to the original raw data. So you have to use an inverse transformation over here. And that will give you the original raw predicted value. So if we refer back to our example wherein we had the values of houses which are ranging from 10,000 to say 10 million, and when we scale them, then the scaled values will range from 0 to 1. And when you train the model and if you do some prediction, the predicted output would be again from 0 to 1, but then you have to again descale it or denormalize it so that it suggests to what range that number represents, which could be in the range from $10,000 to $10 million. So that's why you got to use the inverse transform in that process. This basically shows how to use a min-max scalar. And again, there are methods which which are kind of standard for doing like computing the mean max, like scaling. Then you have the inverse transform, which one can use again to descale a feature.
Yogesh, I think it is still not clear why do you need scaling, why do you need normalization and standardization? How does it really affect the training algorithm if the numbers are going from 0 to 1 versus anywhere in their original ranges? How does it actually affect the training?
So the training, so if one is using an algorithm such as gradient descent, gradient descent makes the iterative, like let me just go back. And so over here, for instance, we are trying to come up with the equation y equals mx plus c, right? So wherein we are trying to figure out what's the value of m and c is. Now, if we kind of if we don't normalize this, then usually what happens is the gradient descent algorithm might take a very, yeah, I think I should have covered this gradient descent before, but just to give you just it, basically the way the iterative fashion over here, you um, kind of jump, like you kind of miss where the local minima that you are trying to find out in that curve is, and that basically just
Why
increases
the
the
local
whole.
minima is going to change if you are doing the
No.
normalization or standardization? The distribution is still the same of the data, right?
The distribution is still the same, but the way the individual features might affect the result output will vary if you kind of don't scale. And I have an example which I'll show in the Jupyter notebook, wherein it shows like if what's the result, what's the effect of not scaling and scaling on the performance of the predicted model. So I can show that in the coming slides.
May I chip in?
Yes,
because
please.
I think I understand. It's very important that Himanshu just did not let this go. So for example, for the linear regression model, for linear regression itself, scaling is not that super important. It might affect the training, but your overall result will be, I believe, the same with or without scaling. It's not true for all machine learning models, and even with. So let's just stick with linear regression. So the animation that Yogesh showed us is just about one feature and one target variable, right? So we just have a single feature, and that is the x-axis, and the target variable is the y-axis. But normally you have, I don't know, a lot of features. So it's a multi-dimensional problem, but the number of independent variables are many more. And just to make sure we understand which variables or what we are scaling. We are scaling the features, each column in our data set, each independent variable is transformed such a way that it typically has a zero mean and a variance of 1. And why is it good? Just imagine you have a linear regression where you have multiple independent variables. After you trained your linear regression, the coefficients, basically the scaling factors, the learned scale, basically the learned m values for each independent variable will give you a hint how important that feature is, how much it affects your results. And if you don't have a scaled feature set, then obviously the coefficient, into that coefficient, this information will creep in. What is the typical magnitude of that feature, which is kind of irrelevant. It won't tell you the importance of that feature anymore, just the magnitude of that feature, which is not that important. Also, Yogesh mentioned that if you use another machine learning model which is based on distance, this is probably the most important or the most typical one is the nearest neighbor. Basically, you are calculating for an unknown point how far it is from known points in the data set. And when you calculate distance, you are going to use typically the Euclidean distances between the features. And if you don't have scaled values, then just the pure magnitude, the typical magnitude that a feature uses will completely skew your distance metric calculated on the features. All right, I shut up.
Okay,
sorry.
great. I think that explains it really well. And I think one key point that you mentioned is that each of the columns or each of the features is being scaled independently of the other features, which
Yes.
is crucial.
Yes.
Okay, great.
Yeah. Thanks, Peter, for filling in. So that was really informative. So next we will have, next we will look into the model evaluation. So I have a small, let me see. So I have a small video that will, yeah, that will explain this model evaluation. So with respect to model evaluation, basically we want to understand how the trained model that we have just built, how is it effective? What is the accuracy of that model? Does it give a good prediction result? So what do you mean by good prediction results? So those are some of the small things that we will try to cover in this video. So this is a video from the Coursera, and that just gives a gist about how to go about evaluating performance for regression models. So we will cover the classification models in next upcoming lectures, but today we'll just specifically talk about the regression models. Please let me know if this video doesn't stream well.
In this video, we'll be covering accuracy metrics for model evaluation. So let's get started. Evaluation metrics are used to explain the performance of a model. Let's talk more about the model evaluation metrics that are used for a regression. As mentioned, basically we can compare the actual values and predicted values to calculate the accuracy of a regression model. Evaluation metrics provide a key role in the development of a model as it provides insight to areas that require improvement. We'll be reviewing a number of model evaluation metrics, including mean absolute error, mean squared error, and root mean squared error. But before we get into defining these, we need to define what an error actually is. In the context of regression, the error of the model is the difference between the data points and the trend line generated by the algorithm. Since there are multiple data points, an error can be determined in multiple ways. Mean absolute error is the mean of the absolute value of the errors. This is the easiest of the metrics to understand since it's just the average error. Mean squared error is the mean of the squared error. It's more popular than mean absolute error because the focus is geared more towards large errors. This is due to the squared term exponentially increasing larger errors in comparison to smaller ones. Root mean squared error is the square root of the mean squared error. This is one of the most popular of the evaluation metrics because root mean squared error is interpretable in the same units as the response vector, or y units, making it easy to relate its information. Relative absolute error, also known as residual sum of square, where y bar is a mean value of y, takes the total absolute error and normalizes it by dividing by the total absolute error of the simple predictor. Relative squared error is very similar to relative absolute error, but is widely adopted by the data science community as it is used for calculating R squared. R-squared is not an error per se, but it is a popular metric for the accuracy of your model. It represents how close the data values are to the fitted regression line. The higher the R-squared, the better the model fits your data. Each of these metrics can be used for quantifying of your prediction. The choice of metric completely depends on the type of model, your data type, and domain of knowledge. Unfortunately, further review is out of scope of this course. Thanks for watching.
Okay, I think that that covers the model evaluation aspect. Let's quickly see a Jupyter example, how to go about doing the min-max scaling. Let me see if I have anything. Yeah, so next hands on. Okay, so over here, I just wanted to show like how to use the min-max scalar API from the scikit library. Over here, I'm just going to walk through like what's happening in the code over here. So we have an input data set, which we are directly downloading from this URL. So we can specify what's the URL is. And again, using the APIs from the pandas library, one can directly read the URL. So that you can see that how easy it is to like start working on the data set, whichever is available online. So you just pass the URL of the data set and it will just download through the API call. Next, we can see that we are calling a min-max scalar through this scikit-learn pre-processing module, and we are calling this min-max scalar function. So that we can specify what is the feature range that you would like to set. So you can set it between 0 to 1, for instance, or you can as well give any other range like 100 to 200 and so on. And then once you call the min-max scalar, then we have something called fit transform that basically transforms the input array that that needs to be scaled, and we can then print the output. So if we run this, then you can see the values of X are now in the range of from 0 to 1. So that's scikit-learn min-max scalar example, how to use it. Let's look at how to use the standard scalar, which API. So again, this is the same one, but over here, the values range, like the input values, which are in 0 to 1. When we kind of scale that, they now, like when you call the standardization API, then the values are scaled in the range with a mean of 0. And that's how we can see that some of the values are 0.5 and others go to 3. So that's how the standard scalar API from the scikit-learn can be leveraged. Let's try to use a Boston data set like what we covered in the last class. We use a Boston data set. Again, the methods over here are the same like what we covered in the last class. So basically we are calling the Boston data set, which is pre-built using the scikit-learn API. And you can see that these are the different columns, like the crime rate, age, and so on and so forth. So over here, if we look at a column called as NOx, which is over here, then you can see the values of this feature go from 0.53 and so on. And if we look at the text column, then the values of text range from like 296 and so on. So if we just try to plot them, then this is how the raw data will look like. On the y-axis you have the text, and on the x-axis you have the NOx. So if we try to use the standardization API, so over here, this example basically shows how you can directly use it without the scikit-learn API. So there is a mean calculation, the standard deviation that is calculated. So that's one approach. Or you can directly use the scikit-learn. So here you can see once we run that, the values are now scaled with a mean of 0. And that's how this values would look like. Or you could just use the Python's, the scikit-learn's pre-processing API to do the scaling. One could also use a min-max scalar with directly using the formula, which is x minus x mean, and we can still get something similar. Here you can see the scaled output is now in the range of 0 to 1. You can use this formula, or again, you can just use the min-max scalar API from the scikit-learn to do the same output. Now let's train a linear regression model using the standard scalar API. So here you can see that there is a target value, which is, I suppose, the price. And then you have the whole input data set with different features. So what we are trying to do is kind of predict what is the value of a house going to be. So let's just use the raw value without doing any scaling. Okay, so, and this is a linear regression. So if we run this model, then we can see that the R2 score for this, again, the R2 score was the model performance, and that the way you can calculate an R2 score is using model.score, which is another like the evaluation module within the scikit-learn. So if we plot that, then we can see that the value of R2 is like 0.74. So that's the model accuracy. But if we try to scale this, then we will notice that, and if we run this, now the scaling value, again, the values would be scaled down to like 0 to 1. So if we try to scale that and try to plot that, then you can see the R2 score is not changed. So this basically shows that scaling not necessarily affects the model's statistics with respect, like the accuracy of a model for a linear regression. But if you have a very huge data set, then it may increase the training time of a model. Now, if we try to look the effect of scaling and descaling on a different kind of a model. So here we are using something called stochastic regression. So over here, so if we try to run this, then we can see that when we are, so in the first case, we are not doing any scaling. And when we don't do any scaling, we can see that the model score is minus 3.8. But when we do the scaling, we get the model score, which is 0.74. So anything which is in the range, the score, the R2 score, which is close to 1, shows that there is a good correlation of that input data set with the output. So over here, we can see that when we are using the scaling approach, our predicted our trained model is much more better in predicting the outcome as compared to not scaling. So this kind of shows like what is the effect or the benefit of scaling the input features. And this is a small code snippet over here, which shows how to calculate the model accuracy metrics. So we talked about, so in that video, there was like mean absolute error, mean square error, and root mean square error. So all these again are provided as an API within the scikit-learn. You don't have to manually write the equations for calculating those. And if we run them, then we'll see something like this. You have the mean absolute error, mean square error, and root mean square error. Any questions so far on this? Okay. If not, I think we have covered most of, and we are almost on time over here. So we have covered the feature scaling today and the model evaluation. Let me quickly show another video, which the topic of importance will be covered in the coming class. So let's look at this. All right, so basically what we are seeing over here is some kind of classification algorithm that goes into like picking whether the fruit or the vegetable over here is ripe or not. So the way it does is some kind of image classification using machine learning, and tries to identify whether the green pepper, whether the pepper is ripe or not. So so that's what we'll cover in the next class, is the classification technique, and try to see few of the examples on how to use classification on real world problems. So with that, we have 3 minutes left. So any questions so far? Okay, if not, thank you everyone for attending this. We will see you in the next class.
Thank you.
Yeah, bye.
Thanks.
Bye, thanks.